I found a really cool game on the iPad this Sunday. It was in church killing zombies. What's the name of this game? Dead Trigger 2. Pretty slick controls. Like a first-person shooter. I actually didn't suck at it. Yeah, it was like weird. I don't know why it's free. But it was I think it's only for iPad. It might be for phone. I'm not sure, but the controls were pretty slick. So I was impressed. So I spent an hour in church killing zombies. I mean, the other parishioners should be thanking me. It was a major invasion that I saved them from. So that's what I told my wife. So you don't want to be dealing with this stuff. You need me to deal with this. All right. So last week we talked. We were talking about what it would take to implement a vacuum tube version of just addition, 32-bit addition. And we saw we'd probably have to do this on a bitwise arithmetic level. So for each individual bit of our 32-bit number, we would have to hard code in wiring that literally added those 2 bits with our circuits. So we had, 9 different outcomes? Or 8 different outcomes, rather. 2 to the third. So if this is on, and this is on for the carry bit, then this is your result, so on and so forth. So you would literally have that hardwired circuit for each of the 32 bits. That gets pretty complex, right? Okay, so now we're probably talking about the computer the size of a medium-sized desk, just for doing something like this. This is the computer for doing an addition. What about subtraction? Another desk. Okay, well, maybe you can reuse some of the vacuum tubes. So you just run wires to the same 32-bit vacuum tubes that are already there, but now you're sending it into the subtraction circuit. So you're still going to have 32 more circuits. Okay, multiplication, similar, blah, blah, blah. All right, so we can see how this gets complex pretty quickly, right? So my question is, and this goes back to something we asked at the beginning of class, I think last Monday. What does a computer need to do in order to be considered a computer? We have this vague idea of what a computer is. If somebody says, is that a computer or not, most of us can look at it and say, yeah, that's a computer. Or no, that's not a computer. But what's the threshold? At what point is something not a computer versus a computer? When we use the term computer, we're usually talking about a general purpose machine, right? Machine that can solve all sorts of different problems. What's it take to be a general purpose machine? Like, we don't call a calculator a computer. We know it's sort of kind of a computer, but we call it a calculator, right? We don't point and say, oh, that's a computer. So what does a computer need to do in order for us to call it a computer? Well, at the very least, it needs to do math stuff, right?
Yes.
Math stuff. What else is there?
Probably need to be able to store some stuff, store some information.
Okay, storage. Probably input output. We need to be able to get stuff into the machine and get stuff out of the machine. When we think about the types of problems, when I say math stuff, what do I mean? Are all problems on the computer solved at some level in terms of math? At some level, yeah. Now, when we talk about our CPUs, what's a CPU again?
Those all the
Well, collection of magic tricks, really. You know, some of those magic tricks are math stuff, but other magic tricks are literally just magic tricks. Like teaching a dog to catch a frisbee or something like that. Okay, so the CPU knows how to do a whole bunch of things. And we need to be able to dictate to our CPU what thing to do next, and then what thing to do next, and then what thing to do next, and then what thing to do next. And if you do enough things in a row, ultimately you have accomplished the solution to some problem, right? So a general purpose computer needs to have a collection here, we'll call them magic tricks. It's to have a general purpose collection of magic tricks that the CPU can do. And we need to be able to somehow direct the CPU to do those things through our input. Tell the CPU to do this, then that, the next thing, so on and so forth. What's a CPU in these early computers? So we talked about how to store numbers. That kind of is our storage thing, right? We stored numbers in a collection of 32-bit vacuum tubes. That's how we stored a single number. We talked about how to do some math stuff. So math stuff like add, subtract, multiply, divide, we kind of talked through that. But what other magic tricks does a CPU need to be able to do? What are some examples of those magic tricks? So this goes back to problem solving. Like if you were creating a list of the minimal things that a human being can do, such that somebody else can come and say, do this minimal thing, then this minimal thing, then this minimal thing, and you've actually accomplished something real, what would that be? What is that list of minimalistic things that a person can do? Well, let's say that we want to take this hat and get it over to the other side of the room.
Except for like instructions step by step.
Well, what are the steps? What does a human being need to do? So let's say, Skippy, let's say you're the person that's going to get this hat from here to the other side of the room. What would be those steps?
Find the hat, pick it up, and walk it to the other side of the room.
Okay, now let's take that into more baby steps.
Look for the hat.
Okay,
Find the hat.
the hat's right here.
Walk over to the
Okay, yeah, now you're going to walk to it. How do you walk?
right foot in front and the left foot in front.
So each one of those might be magic tricks. So if we think of our legs as peripherals, okay, move right leg forward, then move left leg forward. You know, how far forward? Maybe do some sort of measurement or something like that over and over and over again, right? So we have some loop. So while I have not reached my destination or something like that, keep moving right leg followed by left leg forward until I've gotten there, right? Now, pick up the hat. What does it mean to pick up the hat?
Extend the right hand toward the hat. Grab it.
Okay, so now I need to apply pressure, you know, close the hand so I actually can, so I need to receive the hat as input, right? Store it somewhere.
On your hat.
Oh, whatever, store it somewhere. Then I need to travel to my destination, whatever that means, and then I need to move it, output it somewhere. So some things that we might need to do is move from one storage location to another. Add, subtract, multiply, divide. Let's do remainder. So your generalistic math things. What else? Read from storage. Write to storage. Maybe display. And even display is probably broken down into individual widgets, but we can keep it at a somewhat high level right now. The example always comes back to if you've ever seen the Helloworld program in assembly language. It's many, many lines of code. How does it work? Okay, so we have this is our main procedure. This is in a kind of a modern assembly language. So we're going to move. AH is the name of a register, so a storage location. Move into that the value 9. This displays string service, so that is the way of communicating to our processor that we want to display something. Then we have a hello message. Where is that defined? Oh, down here. Okay, so we're going to move into DX the offset of our hello message. That is the place in memory where that message is currently stored. So here's our hello message. We're going to define bytes. So this is like an array filled with the characters hello world. An array lives somewhere in memory, right? Okay, so we're going to move into this other register, DX, another hardware variable, the offset in memory where hello message lives, where it begins. Then we're going to call the DOS int 21H service, that's a hex number, 21 hex, to display messages at pointer DSDX. So that's anything that's currently in this register. The first part of that register is DS. The full register is called DX. So you can use half the register, you can use the whole register. And magic trick index 21H says display whatever's in that pointer, whatever's in that memory address. So this is one of the magic tricks. Magic trick 21H is the magic trick that says display something that's in a memory location. And then we return to the beginning of the stack, which points to magic trick 20H, which says exit program. That's another magic trick. End program. That make sense? And then this is a variable definition. So this would be something where we're writing bytes to real memory. Define bytes, DB. Does that make sense? So this entire program is done in terms of moves. This int is an interrupt, not like int integer. This says interrupt the CPU. And when we interrupt the CPU, what are we going to do? We're going to say, perform this magic trick. And this magic trick says, look inside of this register and display whatever's in there, whatever that is. Make sense? Okay, so that's some assembly language instruction. Remember, what can you tell me about assembly language?
They're weird.
Well, specifically,
It's a 1-to-1 ratio.
1-to-1 ratio. Every instruction in assembly language, every line of code in assembly language relates to exactly one magic trick on the CPU. So here's a magic trick, move. Here's another magic trick, interrupt. Here's another magic trick. Each of these guys, move and interrupt, they would also have a hexadecimal code. But they're in assembly language, there's a shorthand for making it at least somewhat English-like. But at some point, you're going to have a list of the magic tricks the CPU knows how to do so that you can look it up and say, oh, I want to perform operation 21H. I want to perform operation 20H. That makes sense? So return is the shorthand for do operation 20H. Interrupt, do operation 21H, doesn't have a shorthand apparently. Or if it does, they didn't use it. That kind of makes sense? How that all is working? Okay, so we saw the move magic tricks. Move something from one register into another register, or move a literal into a register. We didn't actually see any add, subtract, multiply, divide, or remainder, but we can assume that that stuff's in there, right? Another function in there is called add1, which is like increment. So we could say add1 AX. That takes whatever's currently in AX and adds 1 to it, storing the result back in AX. It's like saying AX++, where AX is the name of a variable, but it's actually written in hardware. It's not a software variable. Read from storage. Well, we can assume that somewhere in this whole interrupt 21H, we had to read from the DX register and then display out to something, right? So think about 21H, this interrupt. This is a magic trick the CPU knows how to do. From our perspective, we don't care how that magic trick's accomplished. Remember we talked about things being atomic? We were talking about race conditions. Okay, for things to be atomic means that they literally happen in one CPU cycle. Can we assume that displaying something to the screen is probably more complex than that? Sure. For no other reason than I'm kind of hinting that it is, right? Well, we don't have to worry about the complexity because that magic trick is built into our processor. That magic trick is indexed at position 21H. H for hexadecimal. So index 21 on my processor of the magic tricks it knows how to do. And at that position is a hardware circuit written somehow that reads from DX, somehow processes what it just read, and somehow displays it to the screen. What does it mean to display something to the screen? If you have a value, for instance, the character array hello world, and you're the CPU, and you have that value, you've read that value in from a memory address, and you want to display that to the screen, what has to happen?
Get it to the graphics card.
Okay, I got to somehow get it to the graphics card. Why? Because the graphics card's responsible for making stuff show up on the screen. Then what's the graphics card going to do? Well, it needs to do its set of magic tricks that takes something as input, processes it somehow, and then ultimately makes it show up on the computer monitor. Well, how does the computer monitor make things show up? Well, it's going to take something as input. So computer monitor is like a giant method, right? It's going to take something as input, and based on what that input is, it's going to turn pixels on and off and set certain colors. This is why older monitors, remember when we had monochrome monitors, either black or white? Actually, some of the early ones were like black or orange. If you've ever seen one of those where the text was orange or something other than white, that had to do with the way pixels showed up. The cathode ray tubes, the CRTs, actually had a gas inside of it, and the gas would have a color associated with it when you applied it to the filament that was on the screen. And one of the common colors, was it argon? I want to say maybe argon. One of the gases that it used inside there had an orange output or an orange look, and that's why those monitors displayed orange. But regardless, in the black and white days and the monochrome monitor days, the reason why they were single color is because that was an easier problem to solve. Things were complex enough as it was. So in that kind of world, what are we doing? We're turning pixels on or off, right? If you've ever, how many of you have ever seen a black and white computer screen? If you look at it, the entire screen is not turned on. It's not, you don't see all the pixels. Like, this is an active matrix screen. And if I'm looking at my screen out here, I can tell even the black pixels, I mean, they're lit. That's a, you know, that is a pixel that is turned on. It just happens to be the color black. Well, in a monochrome situation, the monitor, each pixel is either on or off. When it's on, it's orange, or whatever, it depends on the gas that was inside the tube. When it's off, it's nothing. It's not lit, it's nothing. So what would you see is you would see just the orange stuff. There's actually been kind of a repeat of this technology. What aren't there black and white screens today that are being sold as new devices? Can you give me an example of one? It's actually quite popular.
Is it the Nook?
You're on the right line, yeah. The Nook or the Kindle.
Yeah.
The
Paperweight stuff.
That's it, exactly. Those are based off of our earlier technology from monochrome monitors, with the difference being is once it set it, it powers off. So that's why these technologies like the Nook and the Kindle, the battery lasts forever, basically, or for a very, very, very long time. Because once the text is on the screen, there's no power on the screen. It's kind of like a Etch-a-Sketch. It draws it and then releases power, doesn't need it anymore until you switch pages. Does that make sense? So something that we consider to be old technology is now being repurposed as new technology because it serves the purpose of being able to easily read it in the sun. Are you ever going to have the experience on a Kindle that you have on a Kindle reader? Now you get into the Kindle Fire, which is, basically a full-fledged tablet. Are you ever going to have the experience on a Kindle reader as you will on an iPad? Well, the general purpose experience, no. But if you're a big-time reader, you might say you have a better experience on the Kindle reader. That's the market they're going towards. If you're somebody who reads a lot of books and, you read them on a plane, or you read them out in the sun, or you read them in, wherever you are, the Kindle is the right tool for you, even though the iPad has a Kindle app on it. It's that type of thing. Well, we're using an older technology because that was an easier problem to solve. What I'm trying to get us to do in this final week of class is really put ourselves into the shoes of those early computer builders and think about what it would take to solve those problems. So if I'm designing that piece of hardware, even this whole thing, just this one line, there's so much detail that's underneath the hood of that one line. So yes, it's a one-to-one relationship. That is, I can use one line of assembly code to call one magic trick of the CPU. But under the hood, the CPU is solving a complex problem, right? Very complex problem. It has to talk to the graphics card, whatever that means. Well, let's think back to the early days of that, before drivers. Because at this point, we're talking about machines that don't even have operating systems, right? If we don't have operating systems, we don't got drivers. So it's a chicken or the egg issue, I suppose. So in the early computers, a graphics card had to be some sort of minimalistic piece of equipment, right? Maybe very proprietary in nature. You didn't have 20 different companies making graphics cards. You think back to these early computers, EDVAC, UNIVAC, the gymnasium-sized computers. They had a manufacturer make a proprietary graphics card for them, whatever that means. And the computer was built specifically to talk to that piece of hardware, that piece of circuitry. And for all we know, that graphics card might have been the size of a desk in and of itself. Right? I'm speculating at this point. I don't know how big the graphics cards were, but that wouldn't be like horrifically surprising And given what we're talking about here with rows of vacuum tubes and things like that. So when we have to tell our processor to talk to the graphics card, there has to be some minimalistic standard, or at least a proprietary standard, that is used. And it's going to talk to that graphics card in probably a very complex way. Something that's not atomic, something that's maybe 200, 300, 400 lines of code, of assembly code in order to do that. But the point is, from our perspective, we just got the ball rolling by making this one call. And it talked to the graphics card. And the graphics card talked to the monitor. Well, what's the monitor? The monitor is a bitmap. Our early monitors were a bitmap, so maybe they were 800 by 600 pixels. Actually, the early ones were probably even less than that. 320 by 180 or something like that. Basically, the resolution of the original iPhone. But each pixel was either on or off. It was a digital pixel. So what it did is it went through and decided, okay, well, you're going to display stuff on the screen. Good news for us is the early computers only showed text, because images were way beyond what we're trying to do at this point. So what are we going to do? We're going to go through and all the pixels start off as being off, and we're going to turn only the pixels on to show the text we need to show. That's how monochrome monitors worked. Every pixel was an on or off, 1 bit. Now we think about our monitors, they're 32-bit color, so every single pixel can have one of 4 billion shades of colors, as opposed to one on or off in the early days. So what about, so let's say we have 32-bit pixels in our color today. So every pixel can have 4 billion different shades. There's 4 billion different unique combinations. So every single one of those individual pixels is represented as a 32-bit number, potentially. RGB is 3 bytes, red, green, blue. So each one would be 0 to 255, 0 to 255, 0 to 255. So actually it would be 24-bit for each individual pixel. But we get the picture. 24 to 32 bits, and you're taking up, there's a lot of vacuum tubes going into that, especially if you have, let's take our monitors today. A newer iMac, like we have down there, the screen resolution is, I think, 2560 by 1536. So, $2560 by 1536. I think that's pretty close. That's that many individual pixels. Almost 4 million individual pixels. And we'll say each of those pixels is actually, we'll go with a 24-bit. We'll say it's RGB color. That many bits total. Divided by 8 is bytes. Divided by 1024 is kilobytes. Divided by 1024 is megabytes. Per frame, per screen, whatever. Okay, most of our monitors today are 60 hertz, which means there's 60 frames per second. So 675 megabytes of data per second are represented by our modern computer screen. That's a lot. In our early computers, our monochrome monitors, let's say it was 320 by 180 or something like that. 320 times 180, that's the number of pixels. Each pixel is represented with 1 bit, on or off. so we'll just leave that alone. Divide that by 8, 7,200. Divide that by 1,024. Divide that by 1,024. That's 0.0068 megabytes per frame. And back then, it probably wasn't a 60 hertz monitor. It was probably more like a 15 hertz monitor. But even if we say it was 30 times 30, 0.21 megabytes. So we take 675 divided by 0.21, 3,214 times the size for an individual second of display today than it was in our early monochrome monitors. So when I was a kid, we had monochrome monitors. So this was back in probably, what's the earliest I remember a monochrome monitor? 93, 92, something like that. Not born yet?
I was born
It's like they're laughing. Not born yet. So I think we had an Epson computer in '92. I want to say, and that had a monochrome monitor. So our monitors today, since 1992. So 92, it's basically 20 years ish. Let's just say in 20 years. The power of our monitor alone has gone up by 3,214 times. It's pretty legit. Divide that by 20. That's 160. It's 160 times better per year. So 1,600% improvement every single year. No, 16,000 times improvement every single year. That's pretty legit.
Does that continue for our current years?
Not as much. It's certainly slowing down. But I just read an article this morning. Dell just announced their 4K monitors. So let's look at that. I don't think they're selling them yet, but they're okay. 7680. Yeah, it's like but they don't exist yet. What would I say? 4680 by 4320. Actually, you sure it was 4680? Yeah, 7680. It's like that doesn't sound like it's the right aspect ratio. So that's 7680 times 4320. That's the number of pixels times 24 for the number of bits per pixel, divided by 8, number of bytes, divided by 1,024, number of kilobytes, divided by 1,024, number of megabytes, times, well, just comparing apples to apples, let's go 60 hertz, although some of them might be faster than that now. We have TVs that go 120 and 240 hertz, right? But we'll do by 60. So now those monitors at the same refresh rate are 5,695 megabytes per second divided by 1,024, 5.56 gigabytes per second, compared to 675 megabytes. So times 1024 divided by 675. So 8.5 times better in the last, well, monitors with that resolution, the 675, have been around for at least seven years, something like that. So in 7 years, it's basically doubled every year, something like that. But we're still on a pretty good.
Is there that big of a difference between those two?
Well, depends. I mean, what's the quality? You have one thing is number of pixels on the screen. Number of pixels on the screen designates how many things you can have on the screen at once. Then you have the pixel density, how close the pixels are together. That is what says how crisp the picture looks. So like the Retina displays and the equivalent displays, the equivalent gimmicky name that the displays have on the other smartphones. Whenever you get a display that has close to or more than 300 pixels per inch, that's called Retina. That's called, the human eye can't discern pixels. You can't see the individual pixels. So that's as crisp as we need it before our eyes get better. We can't tell, 300 pixels per inch versus 800 pixels per inch, the human eye wouldn't be able to discern because there's no visible pixels. So now it's just a matter of getting more and more pixels on the screen. Now, this monitor from Dell, I think the 4K one I read about, I think has 226 pixels per inch or something like that, so it's not quite Retina, but, we're pretty small pixels. If a human being looked really, really, really close, you probably could see individual pixels, but kind of just barely. Same thing. You're getting pretty close to having large monitors that are as good as the human eye can discern. So then it's a matter of packing more pixels onto the screen. That way you can get more stuff on the screen at once. But when you do that, and the screens don't actually get physically larger, then everything gets smaller. So yeah, you have tons of windows on the screen, but the windows are going to be too tiny. You won't be able to see them. So that's when we go to bigger screen. So everything's just this whole moving, it's a moving target. More pixels equal more stuff on the screen, need a bigger screen so that we can actually, the stuff's actually big enough to see, so on and so forth. Go ahead.
Why did they go to the 300 pixels per inch?
Oh, because it's prohibitively expensive or impossible at this point. I mean, and that's what, you already see that with the different devices. It's much easier to get a higher quality display in a very small size. And maybe by easier, I mean more cost effective. So it's probably not that they can't do it at the, I think the monitor that Dell announced was a 24-inch 4K monitor. It's not that they couldn't do it, but they couldn't do it and have it not cost as much as a car. It's probably more of the truth, is my guess. Maybe there's some other limiting factors with heat or something like that that I'm not necessarily aware of, but my guess is the biggest holdback is price. Like, hey, you want to spend $25,000 on a monitor? We'll build it. We have the technology, but not something you could throw on the shelf at Best Buy and expect to move. Is the story, I guess. So, but in any case, we can start seeing that writing to monitors today, what our graphics cards need to do, is a significantly harder problem than writing to graphics card or writing to monitors back in the vacuum tube day. And actually, one of the things they're touting with the new Mac Pro is that the multiple graphics cards that are in it are supposed to be able to work together and drive, I think it's either 3 or 4 4K monitors simultaneously. So even if it's 3, we're talking 16.5 gigabytes per second of data running to those monitors, streaming bits. That's a lot. A lot more than what did we say it was for the old computers? 0.2 megabytes per second was for like our monochrome 320 by 160 monitors, something like that. Something fractionally smaller than what we're dealing with today. So it becomes very interesting. going back here, we're really trying to understand the complexity of this single call. So when we say that that assembly language has a one-to-one relationship with the CPU, we don't want to think about it's calling a single, it's referring to a single magic trick on the CPU. But that magic trick could be arbitrarily complex. Somebody had to build it, right? But it could be arbitrarily complex. When you pay to have electricity run to your house, you're paying a bill to We Energies or whatever, and they hook your house up to electricity, and you have power at your house. But I think we probably recognize that whatever's generating that electricity behind the scenes is highly complex, right? Not like one moving part, a zillion moving parts, millions and millions and billions of dollars worth of moving parts that are constantly need to be maintained and all this other stuff. So, that's probably an extreme example, but we can certainly understand that this one line of code that translates into one magic trick on the CPU might translate into possibly thousands of moving parts, if you will, to actually make a full picture show up on the screen, even if it's just text. And now we need to have it show up 60 times a second for a 60 hertz monitor, so on and so forth. So, we can start seeing that the number of magic tricks that the CPU needs to be able to do, even just displaying something to the screen. Go back to the monochrome days with a very small screen. Even if we're having to put 0.2 megabytes onto the screen, what do you think the screens look like on these old computers, these original computers? Well, they might have been vacuum tubes too. Basically a light bright is what we were dealing with. I mean, probably in the earliest days. At some point they probably had somebody build an actual piece of equipment that could show something. But the point is, you probably had this room filled with computing equipment, just a whole gymnasium or something like that. And then somewhere over the corner, you had a little tiny screen. This is your output. And you had these guys sitting there with trifocals trying to read the text that was outputting on the screen or something like that. Because before that, stuff was probably outputting on paper. A printer or something like that, right? That was your output before you actually had a monitor for real-time output. You had to, when you ran a math problem through there, you had to wait for your answer to print. So now we think back to the early days. How big is a CPU today? Yeah, what we think of is probably a square, kind of like this. I know I didn't make a square, but the hand doesn't kind of work that way. You know what I'm saying? But most of that's probably for heat dissipation. The actual die, the actual processor in there is tiny. It's probably probably smaller than the home button on that iPhone. The actual processor. Everything else is pins. If you look at the bottom of that processor, you see all the pin density on the bottom of it. Each one of those pins is wired into the CPU somehow for inputs. Okay, that's the number of inputs it needs to be able to pull off all the magic tricks it knows how to do. So all those magic tricks need to be defined in terms of those inputs. That's why your motherboard has to be able to support the right kind of processor in order for it to do its work. It needs to know how to communicate with that brain. Well, again, these are modern day CPUs are built in terms of VLSI, very large scale integration. We could fit a whole lot of power in something very, very, very tiny. We didn't have that back then. We had vacuum tubes. So imagine having to implement a processor. I mean, if we had to implement a processor that had today's processing, forget about power. Let's just say flexibility. We don't even need to do it fast. We just need to be able to do it. We would be lucky to fit the processor in a gymnasium. So what we think about today as being a low-end processor is so much more powerful than the most powerful processors were back then. Because we couldn't fit them in towns. They wouldn't have fit in a city. So that takes us back to this: is what are the minimalistic list of magic tricks that a CPU needs to be able to do to be really called a computer? What kinds of problems did human beings initially envision computers solving? What's the whole purpose that we have a computer? It does work for us. Human beings are lazy, right? Okay. And it's not just a laziness thing, it's also an efficiency thing. But in the early days, I doubt you gained all that much efficiency. Lots of newfangled technology comes out. It doesn't really make us more productive immediately. A lot of times it's just an easier way of pulling off the same thing that, like we talked I think last time maybe, or 2 times ago, about we have like robotic lawnmowers, right? You don't mow your yard faster than you can mow it yourself, but you don't have to be there. It might take 6 hours for it to mow your yard, but the point is that you could be doing other stuff. Well, I guarantee in the early days of that, they had to have some dude sitting there watching that lawnmower take 6 hours to mow the yard to make sure that the programming was such that it didn't start killing local wildlife and taking out shrubs and things like that. You did not immediately gain productivity from this new invention. You actually lost productivity. What took you 45 minutes to do yourself now was taking 6 hours, and you were probably having to chase down this robotic lawnmower to keep it from killing your neighbor's dog, right? So, safe to say that technology back then with these CPUs was probably something similar. All right, so we'll start off next time trying to hone in on what the minimalistic set of those magic tricks, those early CPUs needed to do, so we can try to fit them inside of a gymnasium. Sound good?